Hello, everyone. Welcome to the Transform Now podcast. I'm your host, Michael Marchuk, and today we're joined by Carina Lainer, a principal at Roland Berger's Advanced Technology Center and a leading expert in quantum technologies, including quantum computing. Carina is recognized as a global thought leader, specializing in quantum sensors, quantum communication, quantum cryptography, and quantum computing, advising clients across high-tech electronics, semiconductors, aerospace, automotive, and more. So Carina also works at the intersection of quantum computing and AI, contributing to the insights on how these technologies together are shaping the next wave of innovation. She actually published a really interesting article that I will leave a link for called Quantum Computing and AI, a Superpower in the Making. She holds an MBA from Hult International Business School and a physics degree from Sorbonne University and Johannes Gutenberg University, Mainz. So if there's ever a time that I feel like the dumbest guy in the room, this certainly is it. We're excited to have her with us to explore how quantum and AI are converging to transform industries worldwide. So, Carina, thank you for joining us today.
Thanks for having me.
So, as we look at quantum computing and the way that quantum computing works, how could quantum computing's inherent uncertainty exacerbate AI's hallucination? Basically, be a double whammy on this.
It's actually an excellent question because it looks at two different threats. And I would like to separate quantum computing and AI in the first step to give an answer to the question. So if we look at quantum computers, they are fundamentally different to the computers which we use today. So for example, the ones that AI is running on. The building blocks of quantum computers are so-called qubits, and in themselves, quantum computers are probabilistic. So they don't use 0 or 1 as bits. They use qubits, which can be 0 or 1, or the superposition of both. And unless we measure the system, we destroy the system. But if we don't measure it, we have a probability of them being in a state. And by that, we get an exponential speed up in computational power that can be exploited for calculation purposes. Now, we can think about it like when we flip a coin, and unless we look, it's either heads or tails, and that's our uncertainty element of quantum computers. So something really positive. AI hallucinations, on the other hand, look at a concept where AI gives you an answer that is either fabricated or that is wrong or that is no proof for. So it's two different things that we are actually looking at here. AI tends to search for data and train for words that sound real instead of actually checking for the real source. That's how the AI is optimized. Now, if we think about can quantum computing actually exacerbate this AI hallucination, the answer is probably not, because we are looking at two different concepts here. One is the concept of how you train data, and the other one is actually how you calculate it physically and mathematically.
Interesting. Okay. So with these speed increases that quantum computing promises for a certain kind of computation, so you're building these computations in for AI, how do these AI models, especially the deep learning, work when you have algorithms that may not necessarily be attached to quantum for AI, especially when you start looking at like these larger data sets, these faster cycles that in the complex text that are going through? What kind of algorithms are you going to see that are going to actually help quantum speed up AI?
So when we look at the speed up of quantum technologies and actually at the development of the last years, we have seen very ambitious targets and very good promises by the quantum computing hardware providers. So if we think back to 2019, 2020, there were claims of millions of qubits to be achievable by 2026 and 2028. So now we have 2026, we haven't achieved that. And the issue in that partly lies in a linear forecasting bias. So we thought that once we are capable to build more qubits, then the error correction also gets better. Unfortunately, this linear forecasting bias trap that a lot of companies fell in that trap. And what happened was that the error correction did not improve, and also we haven't been capable to achieve that scaling that certain companies have claimed at the time. So today, there are still very high technical barriers in order to really commercially viably use quantum computers. Nonetheless, they have positive impact when we look at improving AI algorithms and also looking at how it can help. However, it's still more a mid to long-term optimization problem when we talk about the broad applicability of that. So while quantum computers can actually help to handle larger data sets faster or even at all, they also can help, for example, with the energy consumption that is an issue with AI and data centers today. So if we look at this speed up in computational power of certain quantum systems, for example, to give you a practical one, photonic quantum chips use photons, that's light particles, for calculation. And those photonic chips scale very well in comparison to latest AI chips. So for example, if we take the latest NVIDIA H100 chip and compare that to one of the best-in-class photonic chip processors, we go from 5 trillion of operations per second per watt to 40. So that has significant impact also on the energy consumption. And one thing is that AI and quantum go hand in hand with regards to algorithms, but the other thing is the aspect on how can it also improve the computational infrastructure that we're having today.
So that we bring up the whole power thing is a big deal. Do you think as we look at traditional computing, the H100s, the traditional on-off bits compared to the qubit side of things, are data centers, current data centers, built in a way that they could be transitioned into a quantum data center, or are there specific aspects of managing quantum computing that are different than sort of traditional computing? For example, when you see Microsoft say, hey, we're going to take part of our Azure cloud and transition it over to our new, quantum cloud, or is it not really applicable that way?
It's not 100% applicable because the way how quantum computers are constructed in comparison to classic computers is that it's not just the physics that is fundamentally different, but also the ecosystem. You need, for example, cryogenic cooling systems. You need stability. You cannot have changes in temperature or in pressure. So it's not really easy to say, I just deploy now a quantum computer instead of a classic computer to a data center. So when we look at the infrastructure that needs to change in the future, that is something that data center providers definitely need to look at. For the end user, however, the difference won't be so challenging. We won't have a quantum computer in our laptop in the next years. But so also when we do AI computations today, so if we use ChatGPT, it's not like we have the data center in our house. So it's just connected to a very powerful data center at a certain area. And that's then how in the future probably it will work as well with quantum computers. So we won't have it at home, but we will be capable to connect with it and by that be capable to really improve how we use AI algorithms and machine learning algorithms in the future.
So when we see the way that quantum and sort of classical computing are working together right now, do you see this evolution within AI research to allow both to improve because of the symbiosis, or do we see them splitting in terms of, well, classical computing really has to go one way versus quantum going another way? Or again, I'm not really sure how to ask the question, because I see the potential benefits, but I'm not really sure, as you mentioned, how the physics and how the actual implementation of this actually works in the real world.
Yeah. So to maybe go into a more practical direction to an answer. So the good news is that quantum and AI can go hand in hand, and they can actually be a new superpower. It's just not happening today because the quantum computers are not powerful enough. Still, we have the chance already today to exploit the quantum computers that we have to improve machine learning and AI algorithms. And to give an example, first one I want to look at is generative models. So generative AI models that look at classically structuring, giving a data set and clustering those. And these models can then generate new data samples that then actually mimic the properties of the original one. Here you can use quantum resources to draw samples from probability distributions. And what happens there is basically, in mathematical terms, your Gaussian curve improves, and therefore also your result improves. So generative quantum machine learning, as you would call that, has a potential to provide model improvements to the models that already exist today, and to help by generating new insights and finding patterns that conventional architectures today wouldn't be capable to find. And a second example would be looking at large language models and deep learning, so more complex AI algorithms that look also at neural networks. For those, so typically those convolutional neural networks, for example, are used in image-to-image tasks. So for example, if in medical technologies you want to segment or reconstruct something from an image to, for example, tell this is a tumor in a patient, or you see certain structures in CTs or in MRTs, you scan different layers of data. And those different layers of data are the different pixels. And here today, convolutional neural networks learn from labeled training data. So that is the core difference. You always need a human that trains it and that labels that. So in programming, as you also ask for how can it actually advance AI research, in programming, it helps to use large language models to find the right quantum approach per task. And that then can help in reducing noise. And noise is what we call in quantum terms actually defects. So it's something that disturbs your signal, or it's a defect. And if we use quantum modules and process them in the end, the results that we transfer to the clinician become more clear than the ones without the usage of large language models and quantum machine learning algorithms. So in summary, I see three algorithms, because you asked for great algorithms that have the power today to transform the machine learning and AI world. The first one is the quantum generative learning method. So that was the first example. And that is also then the second one, to use quantum denoising, so to improve filtering methodologies. And the third one is actually the quantum linear solvers. And the quantum linear solvers is something where the computational power of the quantum computer comes to play. Because if we do linear solving, we can still do that on AI. So the more powerful AI gets, the more this is also in competition to quantum linear solvers. However, it helps, for example, in medtech to find better solutions and better correlations because of finding more patterns in pixels. And this could, for example, also be used in satellite navigation or in autonomous driving. So really something that is exploited today in AI and quantum research.
So you brought up a bunch of really interesting, like, current practical applications for this. How much of this is still research versus actual practical application? Because you brought up a bunch of really good applications for it, but are those research, or are they actually being used in the real world at this point?
Yeah. That's the tricky question that also a lot of quantum companies don't want to answer, because if we look at the claims that have been made already years ago on the applicability of quantum computers, many of those things have been proven in the research lab or have been shown as proof of concepts. However, the commercial viability of those is still challenging. And personally, I think that as long as quantum computers don't have a standalone commercial value, they won't advance in a way without governmental funding that they are really usable in economics. And if they want to be valuable for industry, they need to get at this point where you really can create value with them and not just have, oh, that's good to know. I wanted to know this. I could have done it as well with an AI. Now I did it with a quantum computer. That's super cool because quantum computers are new technology. But in the end, I don't create value for my company. That changes if we look at examples where AI cannot excel. So if we look at examples in drug discovery or in material science where classic architectures just reach their limits. But for the other problems, be it traveling salesman problems or others, unfortunately, this has not been broadly deployed. So I challenge the commercial viability of that to date.
Well, you bring up commercial viability, and I will counter that saying that OpenAI is bleeding money like there's no tomorrow, and with no hope in any time in the future that they will actually be profitable. So maybe there's a hope that quantum computing will see that same type of investor enthusiasm to be able to offer that. Based on the way, yeah, based on the way that quantum computing it's always seemed to be on the edge of this frontier that we're still kind of pushing towards. I look at it back towards when we hit the large language models and these general purpose transformers, where that was a leap forward in a way that allowed AI to become not just more practical, but actually usable and in more organizational, like traditional organizations, to support solving their problems and involving in their work streams. Do you see that frontier line getting any closer for quantum computing with some of the research that you've been seeing lately? We mentioned photonic quantum computers and others. Do you see that line coming closer, or are we still kind of like that's still 5, 10 plus years away?
So I think it depends on what we look at in terms of commercial viability and research. So, of course, with a lot of quantum research, no money is made today, but it is still needed to be ready for the day when we have reached the million qubit system. So, an example is if we look at pharmaceutical industry and at drug development, to simulate a single enzyme, you would need 1 million qubits. That is not here today. That is here maybe in 2030 if we now trust the claims that have been revisited. But the issue is once the system is here, it's not like you can deploy it from today to tomorrow. You need preparation to define the quantum simulators, for example, because quantum algorithms also are completely different than classical algorithms. So companies today need to prepare for that. That burns money, and that brings me then to the comparison also to OpenAI, which you made, which is actually an excellent one. It needs fundamental investment until we have seen an achievement. And I like to compare quantum technologies to semiconductors, to AI, or even to nuclear fusion. It took decades of investment winters for those technologies to really prove their commercial viability. With AI, if we think about it 10, 15 years ago, I think we wouldn't have thought about a way in which we use ChatGPT and other ones on a daily basis. So many things have changed. And I do see the positive signs as well on quantum technologies and specifically on quantum computers, also on how the achievements that we have made actually will bring commercial value in the next 5 to 10 years.
Interesting. Do you see, because we've talked a lot about how AI would be operating sort of on top of a quantum infrastructure. Do you see the current AI models and the deep learning models actually improving the way that quantum technologies are being developed?
Yes, definitely. Because if we think about large language models and extracting theories, AI gives us a chance so much in research to find new ways of this is a direction that we could look into. This is a pattern that we have maybe seen in a different technology, and to hint us at ways at where we could do our research. And I think that this is also something that can be used in the advancements of quantum hardware technology. So definitely learnings, but also the other way around. Quantum can also help enhance AI for the future. So I think they really go hand in hand, because if we think about the difference in how an AI thinks and how a quantum thinks. So AI thinks in numbers, vectors, tensors, and weights. And then out of that weight, it gives you an answer in an AI if something is true or not, but we don't get the reasoning for that. Quantum, however, in being probabilistic also supports finding better weighted patterns of probability, and thereby also helps us finding better reasoning for the answers that AI gives us. And if we use that, it actually can help hand in hand to improve both researchers in both fields.
Interesting. So at this point in time, are you aware of this type of research that's going on? I mean, are there places where this type of research is active to a point where it could be made commercially viable?
Yes, definitely. So for quantum computers, we distinguish fundamentally not only between the classic systems and the AI systems, but we also differentiate in the physical way of how the quantum computers are structured and what you can do with them. So there is, for example, annealer systems, which can be used for polynomial problems like the traveling salesman problems. There is photonic systems, which I mentioned, which are the ones that also then have significant impact today on chip technology, among others. Then there is the superconducting system and the ionic systems. All of those systems have different levels of stability and different parameters that define their stability. So I think if we, for example, look in terms of research and are we actually at a turning point, one metric that we can look at is also how much was invested to achieve where we are, and compare that. And if we compare that, we see, for example, that the US dollar invested in neutral atom quantum computers per qubit realized is by far lower than the one for superconducting systems. And although those companies are newer and have not achieved so much qubits in terms of absolute value, they have been better in converting the funding received and also in terms of scaling and error correction. And as we see that the global quantum hardware providers move away from just scaling qubits and looking really at error correction, we do see definitely that the point of this is now where we go from research to actual application is at a turning point. And the other thing is that if we look at the ecosystem around it, we have so many startups that evolve that look at construction of quantum algorithms using AI, for example, or at the building of quantum computational languages, such as we use Python on a classical computer, we use Qiskit on an IBM system. So all of that makes me confident that over the next years, we will be at a turning point where companies really make money with this.
That's very interesting. So one of the things I can't leave without asking you about is there have been countless numbers of discussions about how our current cryptography environment is at risk. And, we talk about Bitcoin, which has fundamentally built into it this cryptography, and the value of Bitcoin, which of course is less now than it was a little while ago, but because there's a substantial amount of funding or value that is stored within this cryptographic world that is now at risk from quantum computing. First of all, is there really a risk there? And second of all, is this something that needs to be addressed sooner rather than later, related to not just Bitcoin, but in terms of our traditional communications that every organization relies on?
Yeah, absolutely. So I don't want to cause chaos here by saying quantum computers is a threat, but it definitely is. So I think we shouldn't neglect the threat that will come from quantum computers once they are more powerful. But the other issue is harvest now and decrypt later threats. So taking data today, being not capable to decrypt it, but being capable to decrypt it in a certain point in time. And this is a serious issue for future digital infrastructures, specifically for banks. What typically also happens if we compare industry to regulatory and to governments is that the cycle of taking decisions fundamentally is different. So technology progress mostly advances way faster than government security and ethics. And in order for companies to be ready for the quantum era, as we call it, where quantum computers are powerful enough to decrypt current cryptography, the time has come now. So the NISC, for example, which is US-based, or the German Ministry of Security, the BSI, have already given and published standardized protocols which they suggest to use in order to secure against the threat of quantum computing. However, that remains in the power of the infrastructure providers to actually migrate that, and migration is costly and it takes time. Now we have partly around the world challenging economic crisis, or we have other challenges from industries where probably investing in migrating new cryptographic standards is not the top priority. So that is an issue. And the other risk that I see besides cryptography is actually increasing bias and the scale of harm of quantum computers. So you have just asked about banks and bitcoins. Another thing that I see for banks, for example, when we talk about the integration of quantum computing to AI and conventional systems in the banks, is the issue of having stronger bias, for example, when it comes to credit scoring systems. Because quantum AI will enable a more aggressive optimization. It will even sharpen finding patterns and become faster, deeper, and also harder to detect in terms of, is this a biased answer or not? So when it comes to AI today, it already is discriminating certain decisions in the banking world. And it could be that quantum computers actually increase that. And specifically in the Western world, we have seen that already with AI, certain governments had issues in treating this gray zone of what is good for society and what is not. We see that now with trials against Meta or other companies that are ongoing. And I think this is something that we see intensified with quantum technologies as well. And there is, last but not least, this element of geopolitical power, because if we look at the distribution of where the leading quantum computing companies sit, it's even more in certain regions which are already powerful. And also there we will have a disbalance of power that even increases in terms of digitalization and usage of new technologies.
Yeah, we've actually seen that already with the current technologies, in terms of either bans on technologies going to specific geographic regions or whatnot. So that's interesting to hear those types of things. Do you think there's any solace in knowing that this extreme technology is still not necessarily at the fingertips of the average organization or even some governments because of its the investment required to make it operate?
Definitely yes, and partly it's a threat on the same side. We have seen already over the last 2 years that there have been export controls on certain components of quantum technology, specifically quantum computers. And the reason for that is that specifically in our Western world, we fear certain countries in the East and Far East being capable to use quantum computers to harm us. Specifically, if we look at propaganda from Russia or from China, those export controls were so strong that they even sometimes harmed us within Europe and the US, because we're not allowed to sell products to another because we fear that something might be used harmful against us. So definitely, I mean, generally, for example, for a superconducting quantum computer ecosystem, you need a general superconducting ecosystem that is similar to the one in the semiconductor world. That does not exist everywhere. So, for example, we don't have a large semiconductor hub somewhere in Africa. So fearing that they might be the ones that might be using a superconducting quantum computer against us is something that maybe today as Westerners we could control, but we cannot control it for every part of the globe.
Right. That makes sense. All right. So switching topics to something that's maybe a little more uplifting. What excites you most as we look forward to the next few years of quantum computing and AI? Because obviously AI changes weekly. It seems like we have new models and new approaches that are becoming even more powerful. When you look at this intersection of quantum and AI, what excites you the most as we look into the future?
So what excites me the most is the speed of change that we have already seen over the last years. And while some of the quantum roadmap claims have not been fulfilled, I see so much positive impact from quantum computers, specifically if we look at the aspect of how it can revolutionize pharmaceutical industry and chemical industries. And I think that these are two such powerful industries to really have a positive impact on all of our health and all of our lives. That how we can use AI already today at hand with quantum computers in those industries is something that excites me. And specifically in my job, looking at quantum technologies every day, it never gets boring. We always see new technologies, new research. And it's not this research where we say, well, that's nice in the lab, but let's prove it out. So we really see advantages here that are tested, and it's not only on quantum computing, it's also on quantum sensors and on communication, where these technologies will change our daily life. That excites me every day.
All right. So last question, beyond the high tech world, because as you talk about quantum communications, which is completely amazing to me, we look at sort of, I would say, lesser advanced in terms of technology environments like insurance, banking, traditional manufacturing, whatnot. Do you see a time, or when do you see the time that these types of organizations would approach the thought process of saying, I think it's time for us now to invest in quantum? Is this something that's 10 years away, 50 years away, 5 years away?
I think this is a question which makes me happy because I can answer that not everywhere, but partly this has already happened today. So in the banking world, for example, when we talk about portfolio optimization, this is something which has been shown as a proof of concept. It is not deployed yet. The reason for that is the stability of the systems and the commercial viability. But I truly believe that this is something which will be better. Also, everywhere where you can make money, companies will invest in developing those technologies. So, for example, using quantum computers for arbitrage technologies or for forecasting financial crises. These are things where there is players, specifically large banks in the US, but also in Central Europe, that already collaborate with the quantum computing companies on finding the future solutions for that. So that is something which excites me. And also in terms of manufacturing industry, manufacturing specifically as well, again, in our Western world is currently undergoing large challenges with regards to performance improvements and also finding skilled labor and labor getting older and older. And everywhere where we can use AI to improve processes, these are where I think we will also see the impact of quantum computers in the future. And of course, in manufacturing industry, the investments are not as high as in chemicals or in pharmaceuticals, but that's because the impact is so much higher. If you find, for example, a new a drug which helps you prevent cancer, it's something else than if you optimize a workflow, for example. However, it still has viability, and that's what makes me positive.
That's amazing. That's amazing. Well, Carina, thank you for joining us today to talk through all this stuff. I suspect I could ask you another dozen questions here that have been on my mind, but I really appreciate you joining and giving us your impact to this. I will definitely link your article to the show notes here so people can read it. And I will look for more publications from you in the future. So thanks for joining us, Carina.
Hopefully there will be some more. Have a good day.
Thank
Thank
you.
you.
Thank you.